Hello everyone, thanks for coming for the second meeting of our Warsaw Quantum Computing Group. Today's lecture will be given to you by Professor Piotr Gawron and Dr. Przemek Sadowski from Polish Academy of Science. But before they start, I will just give a short intro. So as you remember, our first meeting was almost exactly 1 month ago. The Faculty of Mathematics, Informatics and Mechanics, University of Warsaw, and the lecture Introduction to Quantum Computing was given by Rafał Dębkowicz-Dobrzański. And today we meet again, this time in Przestrzeń from Facebook, and we are very happy because our meeting is also supported by Daft Code. There is Veronika from Daft Code. We are very happy that they are supporting us, so if you have any questions about Daft Code, their projects, you can talk to Veronika. We'll have a short break after about 1 hour. So yeah, you can always ask questions. Also, I have another announcement. There is a quantum machine learning contest organized by Xanadu. It's a company from Canada. Recently they released Penelane, which is a world-first programming framework for quantum machine learning. And there are 3 tracks in this contest: education, software, and research. If you want to participate and form a team, please contact me by the end of this year, and we'll try participate in this competition. I guess that it will be easier and better to do it together because we are still learning about quantum computing, about quantum machine learning, so it will be much easier for us to participate together. So the first track is education hour. The goal is to demonstrate quantum computing using strawberry fields or Penelane. These are 2 programming frameworks from Xanadu. The deadline is the same for every track, 30th of August 2019, so we have plenty of time, but it's good to start earlier, of course. The second track, a software award for the best modification, extension, or contribution to strawberry fields or Penelane code bases. And the third track, research award for the best scientific paper that actively utilizes strawberry fields or Penelane. Okay. And we also have plans for the next meeting. It will be probably also here at Przestrzeń from Facebook at the end of January, 28th of January. The lecture will be given by Michał Stęchły. It will be Introduction to Programming Quantum Computers, also using Forest software development kit from Rigetti. And the last announcement is that I'm going to publish on our Facebook group links to some articles, materials from which you can learn about quantum computing. So you can also, of course, contribute to our Facebook group and publish some interesting stuff. So if you haven't joined our group or our mailing list, please do so. We have more than 230 members on our Facebook group, a bit less than 100 on our mailing list. So yeah, feel free to join and also publish some interesting stuff, start new discussions. So let's build our community, and I hope that it will grow and it will be active. So yeah, thanks for attention. So I will give a voice to Przemek and Piotr, and because next week we already have Christmas, so I will take also this opportunity to wish you Merry Christmas and also Happy New Year. And now, Piotr, the floor is yours.
Okay, it's a technical talk. The talk is called Elements of Quantum Machine Learning, because we'll show you 2 ways how machine learning can be done using quantum computers. In one case, it is pretty useless. In second case, it's probably also useless. But nevertheless, both the cases are interesting, I believe. And I strongly believe in quantum computation in the sense that it is a very, very important subject. Yet, of course, we don't know whether it is useful yet. Okay, so we work in this institution, Institute of Theoretical and Applied Informatics, Polish Academy of Sciences, where our group, Quantum Systems of Informatics Group, was established in 2001 by Professor Węgrzyn, late Professor Węgrzyn, that had this vision that computer scientists also should take care of quantum computation, as it is an interesting subject. At the time, it was a pretty new subject. Okay, so the outline of our talk is as follows. I will present a short introduction about quantum computers, the way we usually think about quantum computers. I will talk about postulates of quantum mechanics. It's my way of presenting the basics, the mathematical basics that are required to understand quantum computation. And I believe that mathematics is the language of physics, it is the language of quantum computation, and I want to show you some equations, explain them, but if you do not follow equations, there will be some pictures trying to explain these equations as well. So don't flee if you are unable to follow the equations. This is just basically an algebra, nothing else. Okay, the next topic will be quantum machine learning with quantum circuits, which will be presented by Przemek. Then I will talk about adiabatic quantum computing, and I will show how we use adiabatic quantum computing in our particular problem. Then I will show a little bit about quantum APIs and talk more about what is available on the market. And then there will be some summary conclusions and some news, bibliography, etc. Okay, let's start. Introduction. If we talk about quantum computers, we should usually talk about this kind of control loop. So we have a classical computer, we have a quantum computer. Classical computer controls the quantum machine, and the quantum computer, after it performed some computation, quantum computation, its state is measured and goes back to classical computer, and this loop can be repeated many times because quantum computers inherently are probabilistic, and sometimes our results might not be what we expect, and therefore this loop is repeated many times, even if the algorithm is ideal and the machine is ideal. Quantum computation should be also understood as a physical experiment, which is a good picture to have in mind when working on quantum computation. So, of course, we divide our world into the quantum world and classical world. Of course, the classical world is governed by the classical computer, the quantum world by the quantum computer. But okay, so we have an initial state here of psi. We have a unitary evolution, our quantum program, and we have our measurement, and the measurement results are transferred back to classical world from the quantum world. Of course, what is also as an input to the quantum world are the state parameters, and of course evolution parameters, which is basically our quantum program. And of course, this process can be repeated many times. So this is quite an unusual way to think about computation classically, but in quantum world, it is useful way of thinking about it. Okay, postulates of quantum mechanics in a very simplified way. First of all, we need 4 components. First one is a state. Our machine is in a state. Like classical computers in a state. The state of all the registers of the memory, it is the state of our classical computer. In quantum world, the state of the machine is expressed mathematically as a unit vector in n-dimensional Euclidean vector space. Basically, a vector, a complex vector, and we just have standard scalar product in this space. That's all I want to say here. And usually, we also use one particular basis, a very natural one consisting of only ones and zeros, and of course the one is and just rotating one. This basis it is computational basis, and in quantum computation, most of the calculation is being done using this basis. So whenever I talk about an operator, it's basically a matrix in this basis. Okay, we have this nice language here of brass and cats, and this funny X in the triangle bracket is a cat. The other one is bra, and they are connected by so-called Hermitian conjugation, which means transposition and conjugation of the elements. So if we have a cat, we have a bra, we can form a bracket, which is basically a scalar product. Nothing complicated here. And of course, if we have a state, then this state can be expressed as a linear combination of a basis. In this case, our computational basis. And what we require that the coefficients of this combination are basically of length 1. So they add the square of the modulus adds to 1. And what was already told last time, but I want to mention that if two quantum states differ only by this phase factor to I theta, then they are physically the same. So we cannot distinguish them, therefore we think they are the same. Okay, so that's the mathematical description of these objects. It's basically a vector, a unit vector, with this additional class of abstractions, A or E to the eta theta, this global phase factor that does not causes the state to physically change. We use this nice picture, and if you work in quantum computation, you know what it is. But nevertheless, it is a funny beast. It's a Bloch sphere. It's a representation of our simplest quantum system, a qubit. Classically, we have bits that have states equal 0 and 1, or 1. In case of quantum computation, we have qubits, and these qubits can be in a state that is any single point on this sphere. Let us count the parameters. So we have two-dimensional objects. So we have two complex numbers, but we have the length, unique length. So we have only three values, and of course, because of the global phase, we subtract 1. We have only two real coefficients that describe our quantum state in case of qubit. And these coefficients can be mapped to these two angles, theta and phi, as on the picture. Yep. Mm-hmm. Not so much. Uh-huh.
This is specific for certain process description or something like that. This is actually what happens with you when you are sitting here listening to this lecture. You are evolving, your state is evolving according to the unitary operator u, which is similar to the process.
Yeah. How many lines will be on the next slide?
For people who are dealing with micro world, this is just the way it works. Invented for this. This is just the basic bread and butter of the theory of atoms and molecules and everything else. And that really happens with you, with all of us.
Okay.
No, not on this side. It was the quantum measurement. This is the state, evolution U, and the final measurement. This is basically as it works always. Okay?
Okay, I'm not a physicist. I work in quantum computation for quite a long time. And for me, those are the rules of the game. Those are physical rules of the game, of course. But I don't really so much care about physics behind. Not that I don't like. No, I like physics, of course. But I want to say that what I'm interested in is it is an alternative model of computation. And there are many models of computation that are interesting, based on biology, based on combinatorics, and many other different models. Of course, quantum computation is interesting because it can be executed in a hardware, because it is a physical model of computation, so we can build physical machines that are governed by quantum mechanics in order to perform this computation. But from the abstract point of view, I could imagine different rules of computation that would be not so much interesting because difficult to construct, even in case they would be outside of physics. But nevertheless, for me, those are just rules of the game. So I have slightly different approach. Okay, now we have Hamiltonians. So we have states. So when we have states, of course, we need to evolve these states. And how do we evolve our states? Basically using the Schrödinger's equation, which is very scary for somebody that is not really prepared to see it, the equation number 3. But basically what this equation tells us is that our state in very small amount of time, oh, there's an error here. Sorry, the state psi is missing here. Yeah. Okay, sorry, the psi is missing here. There should be psi here. So basically it is how, okay, sorry. Yeah, I always have this problem with it. Yeah, that's true. It should be psi. Yeah, that should be psi. Sorry. Yeah, that's true. Okay, but basically we have this Hamiltonian that governs our evolution, which is important because for quantum computation, Hamiltonian sometimes is our software, is our program. So the Hamiltonian is the entire description of the evolution of the system. And if we want to know how the system behaves from one moment in time into second moment of time, given a Hamiltonian, okay, basically the solution for this equation is a unitary operator. A unitary operator is interesting because for us it is a quantum gate. So quantum gates are unitary operators, just unitary operators. So those are our programs. And in order to calculate this operator, given the Hamiltonian and assuming the Hamiltonian is constant in time, we just use this matrix exponentiation in order to get this unitary operator shown. So what basically is important to understand that given Hamiltonian, given the moments in time, we calculate these unitaries very easily. And these unitaries are our elements of our programs, quantum programs. What means unitary? Unitary means that it is basically a rotation that doesn't change length of a vector. It is rotation. Okay, so we can picture this rotation for example, in this way. So for a bunch of vectors, from darkest to the less dark, we can show for vector this one and this one how in a subsequent moment of times the evolution looks around axis y. It is an example of a unitary operation in different moments of time.
Exactly the metaphor for the life of the universe. It really looks like that. There is some abstract dynamic vector. Its length doesn't change. So overall the mobility is preserved.
It's a very strong statement because then, of course, our evolution is deterministic. Globally. Not really? Yeah, but it should be outside of the universe. I don't care. I'm not physicist. I can talk anything about physics, and you shouldn't believe me. This is just another example of course, of rotation around the z-axis. That's all. So, and of course, that any kind of rotation is available here, and possible. Okay, this is one way of manipulating a quantum state. There is another way of manipulation, which is a measurement. And mathematically, measurement is just a bunch of projection operators that are indexed. So they have some labels. And we require that these projection operators add up to 1. What does it mean that the operator is projective or matrix is projective? So basically, it squares itself. So when you are on the ground and somebody throws you on the ground, you are on the ground. That's the idea behind. And the sum, the fact that it adapts to 1 is basically the law of total probability in a way. Okay, so our apparatus, measurement apparatus, it is this bunch of projections. And what happens if we want to measure a state psi? We obtain a label associated with this projection operator with some probability, and this probability is in the equation 7. And of course, we can calculate this probability if we know everything about a state. Usually not, but in a computer simulation, for example, we can do it. And after the measurement was performed and we obtained the outcome AI, for example, the state of our system changes, which is very unusual property of a system, because observation of the system destroys in a way and changes it. Okay, that's mathematics and formulas behind. I have some nice pictures that I believe explain pretty well. We have a state here. This state, this arrow, this end of the arrow, this point here, that is square root of 0.7 plus the square root of 0.3 times I. And we have 2 projection operators here. Basically, those are questions for me. Question whether my state is ket 0, or projected onto 0, or projected onto 1. And of course, our probabilities here are 0.7 and 0.3, depending on our label, in this case 0 or 1. And after obtaining the label 0, the state will be in, the system will be in this state, at 0. After label 1, we'll obtain this state. Which basically, the measurement changes our state. But it behaves at this moment, it's not really, the qubit behaves like a coin in a way. What's important is that we can ask a different question about the qubit. So we have the same state here, but we have different measurement apparatus and different questions. We ask whether a qubit is in this way or that way. And of course, the labels we obtain are different, because this way is labeled plus I, this way is minus I, and probabilities are like this, numerically calculated numerically. And of course, the state after the measurement is changed in a different way. Okay, allow me to show it, demonstrate this principle in a way, because it is a single principle I can demonstrate you with very simple part of material. Okay, so Przemek has 2 polarizers. Polarizers are everywhere. It's nothing special. Those are just very simple polarizers. And of course, we know what happens. If those 2 polarizers are perpendicular, then no light is coming through. This polarization can be understood as a state of a qubit. 0, 1, plus 0, 0 plus 1, 0 minus 1, and circular polarizations cannot be expressed using these polarizers, unfortunately. So it is 0 plus I1, 0 minus I1. Okay, so the question is to the public and those that are not physicists, what will happen if I add an additional polarizator on this angle here? Okay, nothing changes, apart of the fact that it's not perfect. Here. And in between? No physicist, who knows? How much? I mean, in ideal case. No. Okay, so yeah. Okay, so basically some light should pass through. This can be polarized too. I mean, this screen can be polarized too. Do środka. Yeah, so basically, unfortunately, this screen might be, probably is polarized. But of course, and what is that? That's the effect of measurement. Because the light we have here is not polarized, so the first filter passes only the ket vector 0. The second projects onto 0 plus 1, and the third projects onto 1. So we can observe this effect of projection and measurement with the naked eye in a way using these polarizers. Okay, the next component we need, a part of evolution, is to how to compose systems. Okay, if we have two qubits, for example, and we want to compose them, what do? We use tensor product. Well, okay, tensor product is a fancy name for this kind of operation that we apply to matrices, that we take the first element of the first vector, multiplied by the entire second vector. We take the second element of the first vector, multiplied by the entire second vector, and we have this four-dimensional, in this case, object. And this four-dimensional object is just a state of 2 qubits. But let us write down this kind of state, which is a perfectly legitimate state, 0, 0 plus 1, 1. And of course, if you want to express this state in this form here, equation 10, then we just write it down like this. We compare our coefficients. We write down our coefficients, and we have a what? A contradiction. So basically, we cannot write down this state, this particular state, so-called Bell state, as a tensor product of 2 qubits. This leads to entanglement. This is an entangled state, and many believe that these states are essential for quantum computation, which seems to be true. And that's the study of these states is an entire subfield of quantum information theory or quantum mechanics. But that's basically all I wanted to say about it. Okay, so now we slowly drift towards computation. And if we talk about computation, we usually talk about gates. Like in classical computation, we have XOR gates, NAND gates, or and negation, etc. We have all these kind of gates. And also in quantum computation, we also talk about gates. Those gates are mathematically unitary operations. And we basically need only 2 kinds of gates if we want to perform any kind of quantum computation. First kind of gate of this gate is 1 qubit rotation. This is just a parameterization of a way of expressing this gate in a form that is tells us about rotation about one axis, rotation about second axis, and rotation about the first axis once again. And using these 4 real numbers, we can express any kind of unitary operation on 1 qubit we want, with global phase, which is sometimes important, sometimes not. It depends what we do. These kind of equations you have to understand, and you have to know, and you have to work with if you want to program quantum computers. At least it is what I believe. So that's basically the basic language of quantum computation. Okay, one of example of this kind of gates is a Hadamard operation. Hadamard operation is like a magical trick that transfers our ket 0 into superposition of two states, 0 plus 1, or ket 1 into 0 minus 1. It's basically rotation about around this axis, the axis y, as we can see here. And this gate is usually the first step of many quantum algorithms because it makes a flat superposition of quantum states, and then you can perform some further computation like in Groover's algorithm or many others in adiabatic quantum computation too. So a part of unitary single qubit unitary operations, we should also have at least one 2-qubit operation, for example, C0 gate. So that's basically, for a computer scientist, is a truth table for a 2-input, 2-output gate. That what it does. For the first output, we just copy the first input. And for second output, we do XOR over inputs. Why is it interesting? Okay, in a sense, in a classical computation, this kind of gate is nonsensical because why do you want to copy the first input? It is important because this gate represents a permutation. And permutations are reversible. And this is what is important in quantum computation, that our operations have to be reversible because it is how quantum mechanics works. It is an example of 2-qubit unitary operation, at the same time permutation. So having only 1-qubit operations, general operations, and 2-qubit gate, it is sufficient to perform any kind of quantum computation. And it is what basically now is being done in hardware. Okay, when we draw our quantum programs, we usually draw them using circuits. In a similar way like we do it in classical computation, sometimes we have these large nets of logical nets that describe our computation. Here, we have this kind of circuits. What does it mean? Okay, so we have 2 qubits that are composed in parallel and then composed in series. On the first qubit, in this very circuit, we apply Hadamard operation, so we obtain the 0 plus 2 plus 1 state. The second one does not change. Then we perform C0 operation here. So if this first is 0, the second does not change. Okay, well, 0 is 0. If the first is 1, the second becomes 1, and we obtain a Bell state. As I already told you, an entangled state. And that was something I did in 2016 in May, and ran it on then accessible, the only accessible quantum computer, IBM 5Q, and I got these statistics of measurements, which is pretty good, and it was mind-blowing. It was at the time, after 15 years of my work in quantum computation, that I could for the first time access one of these machines. Of course, today, only after 2 years, there are many other machines, many other frameworks, and many other ways how we can do quantum computation. And so, but for me it was a milestone. So the quantum era, in a way, started around this time. Of course, I mean, for general public, like in laboratories, it was already accessible for quite a longer time. So now the floor goes to Przemek, and Przemek will tell you how to use gate model and quantum computation based on gate model to perform some classification.
Thank you. Hi again. So yes, my goal right now will be to switch to machine learning example with quantum circuits, and I will mostly try to show you what is the simplest thing you can do with it, so that you get some interesting results, and how you can really start. What that you can make one single step towards building something more complex, but where we can begin. So first of all, what do I think about when I will be talking about quantum machine learning, right? Because there are many different approaches. So what I want to talk about is the situation when we try to use a device that is in principle quantum mechanical, so that we can have quantum information processing, but we want to use it for a task that is kind of classical, so that the training set is all classical data and we want to learn some classical features about it. There is no quantum data that we put into this algorithm. We want to solve any problem that we can encounter in real life, but the only quantum part is this quantum information processing device, okay? And what I will be talking about is based on a paper by Maria Schuld and other authors. So we made a little contribution to that idea, and I will show you this in a way that we develop it. But if you want some more detail, that's the best way to start. And this algorithm recovers exactly one of the classical algorithms for classification, right? So the goal is not to get something beyond the capabilities of classical computers. We simply, for a start, want to obtain exactly the same thing and show how we can do that with a quantum computer. And let's introduce some formalism, right? So what do I really mean by building a classification algorithm? I assume that we have some kind of a training set, right? This may be pictures of cats and dogs, and we want to then, given some new image, tell which class is it, right? So we label, I use notation xi for all of the samples in the training set. Then each of them has its individual label yi, which is either -1 or +1, which is convenient in this setting. And the goal is to predict the label of a test element. So the classical algorithm that we will try to implement is based on some so-called kernel function. So we measure similarity between the new element and the elements in the training set. And based on that information, we want to guess, is it more like a cat or more like a dog? In this setting, is it -1 or +1? So mathematically speaking, we have this formula for similarity, which is just norm of difference between the vectors. And then we sum the similarities in both of the classes. And if the similarities are higher within the class with a minus sign, so the whole sum will have a minus sign. Okay, so the sign will be -1, and the other way around. And now we want to figure out how to get the same result with a quantum machine. So we start with assuming that our training samples are unit vectors, so that they map one-to-one to quantum states, right? That's important to use the same notation in this formalism. And then we prepare something very similar to the Bell state that Piotr was talking about, so that we assume that our initial state is in a very specific form, so that we are given a state that encodes this information about our test element, and also we have encoded, we pick one of the training elements and we encode this information also in a quantum state. So what I want to stress is what that really means, right? Because now we have also two registers, just like in the Bell state, okay? So let's think about it for a minute. What exactly do we need to encode this in a quantum computer? And let's say we have our elements are in a space that requires 4 qubits to encode it, okay? So we need 4 qubits to encode a test element, right? And then our training elements are from the same space, so we also need 4 qubits. So how many qubits do we need to encode the whole state? 5. Okay, so to be clear, right? Because we don't encode the test element on 4 qubits and then the training element on 4 qubits, because it's the same register. It's just in a superposition. Okay, so because before we go on, so that it will be, it's one of the things that you really need to understand to think about how it works, okay? So what this means basically is that we have, if we look at the first register, we have some probability of measuring 0 and some probability of measuring 1, right? Just like on all of the previous slides. And then, yes? Yes, okay, I forgot to talk about it because in the previous slides there was always a tensor product. So if I stack two states together, I mean by that there are 2 registers and there is a tensor product between them. Okay? So if we only look at the second register now, there is 1 register, but we have some probability of measuring in a test element value and then some probability of measuring training element value, okay? So we assume that that's our input, okay? So how do we then translate the classical algorithm into quantum device? So we use a very simple trick, really. So it's really the simplest thing that you can do in this field. And we apply, again, a Hadamard operation. And it's very convenient, exactly because of the fact how it's built. And that's also the reason why it's so popular, because it takes 0, one single state, and make a superposition out of it. And what's important, it allows us to create a sum, or allows us to subtract different vectors. And as I said before, the classical algorithm is based on how similar the vectors are. So it's based on how long the difference, the vector that results from subtracting one from the other is. So this is exactly the kind of operation that we would like. This automatically gives us some operation on these vectors that's useful to us. So we take our initial state, which is, as I said, this 0 tensor product element, test element, plus 1 tensor product, one of the training elements, and then do Hadamard operation. And one of the reasons why this notation is convenient is that everything is linear, right? So we don't need to multiply vector by an operation. We can take every term we have and then apply the Hadamard operation on that element separately and then see what happens, right? So 0 is transformed into 0 plus 1. 1 is transformed into 0 minus 1. And everything's linear, just add everything together. So what do we obtain? If we now drop the parentheses and see what happens, and then group the elements together so that we have everything that's connected to 0 on the first register together, and then everything that's connected to 1 on this first register together, we have exactly what I was talking about before. So summation and subtracting vectors. And that's exactly what we want to have, right? So now, if we perform a measurement, what happens to the first register? If we only look at the first register, we get 0 or 1 with about 1/2 probability. That's what we should have. Okay, so I cheat about the probability, but the principle is we get either 0 or 1. And if we get 0, as Piotrek said, the state of the system changes. So now it becomes 0 on the first register. And then, because we have this correlation, we also know that the state of the second register is the sum of the 2 vectors. okay? And the same applies to the second term. If we get the 1 on the first register during the measurements, we know that the second register is now prepared in this state. So how do we use this? As I said, I was cheating about the probability, because now these are not unit vectors, okay? If these vectors are similar, then the length of these vectors will be larger than the initial length, right? And if there lies on the opposite sides of the circle, it will be close to 0. So now the fact whether these two vectors are similar or not affects what's the probability of the output at the first register. And it's linked directly, so that if we now get this initial state, apply the Hadamard operation, and obtain this state, we know that if we get 0 as the results of the measurements, the probability of that event is exactly equal to the similarity measure that we chose before. So if we now follow these steps, we get exactly the same results as we would get if we applied the classical algorithm. Now, just instead of getting a number, we have something with this probability. One thing we can do is to make it kind of hybrid, run classical quantum, so that we get a test element. If it's not unit vector, we normalize it, and then sample training element from uniform distribution, and then do a comparison with only one sample. And then if we don't get the result that suggests that it's similar one to the other, then we repeat until we find one that is similar to the test element. And that procedure gives exactly the same probability of success, the same accuracy, but does not require to build such a large quantum system. So how does it work on some real data? So let's say we consider iris dataset. Okay, some of you may be familiar with it if you tried anything with machine learning. So in here, on this plot, we only have 2 features. There are, in general, 4 features, I guess. And what we have to do in order to apply our algorithm to this dataset. So as I said, we only can operate on unit vectors. So first, we can normalize the whole dataset. Then we can normalize it so that everything lies on a unit circle. And then so that any training element and any test element that we take is a unit operator, is a unit vector, right? And then we can perform an experiment. And if we run it on, this comes from a Rigetti quantum computer, then obviously the results are not as good as theory predicts, but it's not 1/2, right? Everything is closer to 1/2 than theory, but it's still, we can still recognize what the answer should be. So with this, we only get something very similar to the classical case, right? It's quite simple to understand, so it's good for a first step, but it gives us nothing more. So what can we do with it? One idea that we have is that once we have everything encoded in quantum information, quantum states, and everything is done on a quantum computer, we can imagine a situation where these states are transmitted as a quantum states in some network, so that any party only possesses some information that doesn't want to, and he doesn't want to share it with others, right? So because just because we encode this information in quantum states, give us some nice features like no cloning theorem and so on. And then if we go with this and try to imagine how this would work if there are many parties, we can create very similar procedure, and that gives exactly the same probability of classification and allows us to design it in such a way that the information about the training set is never contained in one place. So it's distributed among many parties. They don't have to send it to each other. They only exchange quantum state, and the probability of classification at the end is exactly the same. So once we start developing the quantum versions of classical algorithms, we can then try to add new features that come solely from the quantum features of the system, and then try to benefit them. And that's all from me. Yeah.
Well, thanks, Przemek. Thanks, Piotr. And we'll do a short break, 5 minutes. So if you have any questions to our great speakers, then it's also time to ask. Okay, so please take a seat. Let's continue. So Piotr will tell you about adiabatic quantum computing and applications of adiabatic quantum computers in machine learning. Also about D-wave quantum annealer. And by the way, I have also another announcement to you, because in March, on 14th and 15th, there will be tutorials and workshops of this D-wave quantum computer here in Warsaw within Supercomputing Frontiers Europe conference. So there will be also announcements later in January and February. But yeah, I think that we already all published information on our Facebook group as well. So yeah, Piotr, please continue, and then we'll have time also for questions.
Okay. I'll try to be brief because we are running out of time a little bit. And I will focus on the adiabatic quantum computing and this quantum APIs. I probably skip. It's not really so important. That's important. That's the idea. In order to understand why we do adiabatic quantum computation, we have to start with the idea of classical Hamiltonian. What's a classical Hamiltonian? So basically, it's a function that maps strings of ones and plus ones and minus ones into real numbers. This function h has some parameters hi and jij, and this is a linear parameter. This is the a quadratic term for our function, and basically it's a function that takes a string, returns a real value. Why it is interesting? Because in generally solving this what means solving, finding minimal argmin, the minimal value, the string that minimizes this function is generally NP hard, and appropriate related problems NP complete. So should we have a machine, a black box, that is able to find the minimal value or string that minimizes this Hamiltonian, we would be able to solve NP complete problems. So it is an interesting task. And actually, nowadays, this Hamiltonian is becoming a way to program some of the existing computers. A part of D-Wave I'm going to talk about in a while. There are different computers, classical computers, such as Fujitsu and Hitachi, and I believe a couple of others that also approach this problem. So basically, this kind of description of a mathematical description of an optimization problem is becoming a way of performing computation today. And why it's interesting? For example, we can use we can encode our traveling salesman problem in this way and use, for example, classical annealing algorithm to find maybe not a minimal solution, but a low energy or low value solution for our TSP problem. Okay, what's going on here? Now we move into quantum Ising Hamiltonian. which is a complicated beast, but I'll try to explain what's going on here as best I can. We have two Hamiltonians, quantum Hamiltonians now. One that is similar to our classical Hamiltonian in the sense that it has HIs and JIJs. And rather than having binary values, we put here Pauli operators. So we put here some special kind of Hamiltonians, for example, Hamiltonians, which are Pauli operators. And we have this part, H0. H0 is a local Hamiltonian, local because there is no interaction between two values. That is in a different direction than this problem Hamiltonian. Hz, it is this direction, up, down. Sigma z is up, down. Sigma x is left, right, let's say. Why it is interesting? Because this Hamiltonian is considered to be easy. I will explain later what it means. This one is hard. Now we have a parameterization here, ht, where t goes from 0 to 1. And of course, if the t is equal to 0, this term dominates the equation. If t is equal to 1, this term vanishes and this term dominates. Okay. Why? What's easy, what's difficult, and what's interesting here? A Hamiltonian is a Hermitian matrix or operator. Therefore, it has a real spectrum. So its eigenvalues are real. Therefore, we can order them. Therefore, there is a minimal value. Maybe degenerated, but there is a minimal value. Therefore, we can talk about minimal energy, because usually with these eigenvalues of Hamiltonian, we call energies. Minimal energy and minimal energy state or vector. So ground state or ground subspace, actually. So we have this eigen equation that describes our system. So we have energy values and associated quantum states. The ground, the lowest energy, the highest energy, etc. Which is a way we think about this problem. Okay, so now the easy part of Hamiltonian, this easy part is easy because we know how to prepare the minimal energy state or ground state of this Hamiltonian. It is easy to do in a machine, for example. And then we slowly change t from 0 to 1. So we rise the importance of this Hamiltonian and lowers the importance of this Hamiltonian. And we end up only having this Hamiltonian. And if we do it slowly, the Adiabatic theorem tells us that we will not leave the ground energy of this entire family of Hamiltonians. So we will end up in the quantum state that has minimal energy. Then we can just measure this state using our sigma z measurement, so up or down, and obtain plus or minus 1 values that are solution to our original original problem that we want to minimize. So let me repeat. We start with the idea written in a classical way. We just map it to a quantum machine. We start with this Hamiltonian that is easy, or the ground state of this Hamiltonian, which is easy, and slowly go here, obtain ground state of this Hamiltonian, which is, generally speaking, difficult. And as you can see, it is a kind of magical procedure that allows us to solve NP hard problems, which is not true. Why? Because, unfortunately, we have to go very slowly. this tau value has to be very large in order to perform this computation perfectly. Let me show you a short presentation of this idea, why this tau has to be slow. It is a particular 8-qubit Hamiltonian. And what we see here is the spectrum of the initial Hamiltonian and the spectrum of the Hamiltonians we have in between, and the final one. The thickness of the red line is the probability of being in the ground state, of being in a given state associated with a given energy. And here we have a probability of being in a ground state. So if our tau is equal to 1,000, large, so we go very slowly, then we end up in a ground state pretty efficiently with probability 1 or almost 1. If we go slightly faster, I mean slightly, 10 times faster here, the probability goes down. And we have some probability of ending up in the second excited state. So in terms of computation, our solution is not as good as we want. It's not the optimal one, but it's just slightly worse than we could get from the perfect in the perfect case.
And very often what you have, this Ising model actually was created to describe, first of all, it's in a space very often on 2 dimensions on the square lattice, and imagine that on each point on the lattice you have spin. So spin can have 1 and you can have ferromagnetic or antiferromagnetic depending on the value of J. And suddenly from non-interacting you just throw spins on this lattice and you have some sort of random arrangement. Then you start switching and you have this adiabatic, and that's exactly the value of J tells you what's the first excited state.
Mm-hmm.
And then you said that it's a magical trick to solve it, but it's not. Whether it's NP, whether it would be a magical thing to solve NP problems would be not how fast it is, but how does it scale, like the complexity.
Yeah, but when your system becomes larger, this gap becomes smaller, and this gap is important. And this gap tells you how fast you can go. Because if you go too fast over a gap, then your solution will smear, like here. You can see that when we go very fast, then you are likely to get into higher energy states, and even faster, then it just blows up, and it's not really important.
Magical with respect to this gap. This is the same gap which makes this chair stiff. If it would be just a collection of charges, first of all, it would collapse by itself, but it would be also perfectly elastic, so to speak. Now, what makes it impossible, really, for me to bend it is that all atoms there are in the ground state, and there is an energy gap. So in order to force bending, I have to introduce a lot of energy to let all those atoms to go to the higher excited state. It doesn't matter whether I just add a little bit energy, nothing happens. That's why basically everything exists around again. Now, if I want to add a lot of energy, I have suddenly attack this, right? Okay. And this is how, in somehow magic way, the time scale is related to the energy which is delivered normally. And if you just do it very, very slowly, adiabatically slowly, and the system does really have energy gap, because there are unfortunate systems which does not have, and that's another story, then you are guaranteed by this adiabatic theorem to end up in a Hamiltonian, which is to the state which is in ground state of this complicated Hamiltonian. And then you can use it to solve you can measure properties of this ground state to solve your problem.
Okay, for me what was magical is just basically to say that if we didn't understand the entire physics behind it, we could just say that we know how to solve NP hard problems using quantum computers, which is not true. But of course, we have to care for physics. Okay, so there's a machine whose picture I have slightly later, called the wave annealer, that basically implements this model. We believe. There's a lot of belief here. But nevertheless, it's an interesting physical system consisting of nowadays 2,000 qubits connected as in this very strange way called chimera graph, which basically allows us to perform this annealing, not perfect, but imperfect one, and obtain some results which are, I can in a way convince you, are not insane. That's all I can tell from my own experience. And so basically how this value of this Hamiltonian changes are given on this plot, which is not very important here, but basically this kind of machine exists, and we try to use it to solve our computational problems and to assess its usefulness for purpose. In our case, satellite image processing. Okay, hyperspectral image processing or satellite image processing. What's the problem here? And that will be a slightly technical example, but it will explain how we can use this machine for performing useful computation. A hyperspectral image is basically an image consisting of pixels, where every pixel contains information about the spectrum, slightly wider than visible light usually, which is near infrared, slightly ultraviolet, and it is divided usually into 100 to 100 bins. So rather than having 3 values, we have 200 values, and these values are just basically the intensity of light in a given bandwidth of energy, of photons. And when we do this kind of experiments with this kind of data, usually we are given a ground truth, so somebody tells us what is on the ground, and we would like to somehow have a method to learn or to teach an algorithm to understand what's on the image. And it's a very usual problem. Those are some pixels. Those are just some pixels. Each line is a single pixel, chosen from the red area and chosen from the green area. Just a couple of pixels. Yep. So usually we are just given a couple of examples, let's say 20 of examples for a given class on a picture. I would like to train our classifier in order to be able to recognize the entire picture as best as we can. That's the idea. And how we do it using the wave, we do it as follows, in a pretty easy, straightforward way. Okay, so first of all, we normalize the data, which is the usual step in most of the classification problems. Then we decide to work with one versus all classifier method. So the problem here is of course that we work with qubits. Qubits give us binary outcomes, and we have to deal with a lot of classes. It's like 16 for this particular image, but more than 2 basically. So our approach is typical for example SVMs. So we use a one versus all approach that is pretty well known in machine learning, but we add this quantum annealing step in order to enhance our classification procedure. So we take our training set, which is basically a bunch of pixels with known labels, into a given class, C, and the rest. We train a binary SVM using this data and these labels. We calculate probability of a given pixel for the entire image of being in this particular class or not being in this class. Then we transform this probability into energy in order to build our Ising model. So we transform this into energy. So the very high probability is high energy, low probability is low energy, and we build Ising model. This Ising model has has a meaning behind it. So, so HI means that's my likelihood or my energy of being in one class, particular class. This beta parameter tells me how strongly my neighbors want me to be in their class. So how strongly my neighbors push me to be in the same class as them. And of course, we want to agree this information somehow by finding low energy solution for this Hamiltonian, which is in terms of Markov random fields, and if somebody works with image processing knows that is a maximal a posteriori probability of a Markov random field, basically. Whatever. It's not really so important here. What happens, we then take this model, abstract model, embed it on the, and of course it is on a grid. So in the sense that the neighborhood graph is given by a grid, regular grid, image. And we have to embed into chimera graph, which we do okay, in a clever way that was already known before we found it. But basically we use 2 pixels per, 2 qubits per pixel, and we assume that those qubits will agree. Then we sample a couple of low energy solutions from D-wave. In our case, 10. It should be more, but it was 10 in experiments. Then we transform the information that was obtained from D-wave into grid model back again. And then we just calculate in how many energy our samples, our pixel was belonging to this class or not. And we build new probability from this information. And then if we do it for each class, then we combine the information from all the classes by just applying argmax, which is a principle behind one versus all classification. Okay, some results. So what we can see on these pictures is basically those are 4 classes for a very small patch, 32 by 32 pixels. It is what we can do now using a single application of a quantum computer, or D-wave annealer. And so those are our classes, 4 classes. X, it is our training sample. And what we do, first using these x's, these points denoted as x, we train our probabilistic SVM, and we obtain our result of classification from this probabilistic SVM. It is the second column. So basically, that's the probability of a pixel belonging to a given class. Red, high, blue, low. And then we transform, we apply this algorithm and anneal our result, and we obtain this kind of classification, which basically I can say it's sane, in the sense that it is something I would expect from a good annealer. We can see that not all the samples are the same, so this differs slightly, but those errors are not completely noisy. It's not a random thing. Basically, kind of works. And of course, we vary our parameter beta here, which means the peer pressure of a neighboring pixel on our pixel. And we can see that with higher beta, larger clusters appear, which is something we should expect. Spectral information is used only to train and test the SVM. What do you mean by how much? I mean entire pixels. All the bins, all of them. We should probably extract some of them because of the physical reasons, but yeah, that's the reason. Here I have one class versus all. So that's my first experiment, second experiment, third and fourth, and then I combine the results in this picture here. So I just test whether I take my single class versus others' classes. And I do it for every class. SVM is trained with a single bin in the single pixel, which means like a single spectrum. So my features are my intensity of my spectra in a given bin. Kind of works. That's okay. I can tell now. I have no better results to show you. We're working on that. I don't really care right now. It's not my goal. My goal is to just to convince myself that it's not crazy what I'm doing. That was my goal here. Now we applied for a grant. I will do proper comparison with proper experiments and time assessment and quality of results, etc., etc. But it's not something that is done yet, unfortunately. But if the guts of the National Science Foundations are positive towards us, we might get this grant. And response to your question, let's say in a year or two, rather two. Okay, so that's basically all we do with the D-Wave now, right now. Not all, but one of the things I like. And it shows you how you can apply D-Wave in a kind of real-life problem. Okay, quantum APIs. What time do we have? Okay, we should finish, should we? Okay, 5 minutes. So basically, I wanted to here to show you there's some important, like what is available on the market. If you are nerds and geeks and you look on the internet, you probably know it already. IBM has this QA-Skit, which is a nice library. We should look at Aqua module, which is interesting because it allows you to build high-level algorithms on a gate model quantum computer they have, which is pretty interesting stuff. There's this Google Cirq library connected to OpenFermion. OpenFermion is for chemical simulation and finding, basically analyzing quantum chemistry. I don't know much about this idea. Unfortunately, the chip, the Google chip is not available for mortals, only for Googlers, as I understand. There is this forest library by Rigetti, which you will learn more in like a month. So I'm not going to go into details. Rigetti is kind of available for people, and they are willing to cooperate with some people. So it's relatively easy to use the software. And there is this D-Wave Ocean SDK, which is very interesting because a part of doing this very simple naive things that we do, you can build a more complicated problems with this SDK, and then divide your problem into parts that can be run on the D-Wave machine. So D-Wave machine can solve your problem if you have only 2,000 variables, but using this Ocean SDK, you can run larger problems of 20,000 variables, for example, and anneal them. It is a hybrid quantum classical algorithm then, but it's nevertheless interesting. And what they do now, it's pretty nice. Okay, this is just a picture of the D-Wave machine, probably one of the old ones. Okay, some conclusions. There's some buzz and news, and basically our landscape is changing all the time. One of the information is that D-Wave claim to have 5,000 qubits in a new annealer and 40,000 couplers. Probably that's the Pegasus architecture they were hinting for quite a long time, for a year at least. So it might be interesting. And there is this new quantum device constructed by IonQ, this quantum computer based on ions, which is a different architecture, completely different architecture from Rigetti, D-Wave, Google, and IBM. They claim to have 160 qubits, but they can perform only operation 30 in a given time. So it's kind of complicated, and I don't really know the details. Apart of that, there is a nice place to visit if you want to play with software, Quantum Open Source Foundation, organized by people from Canada, basically from protein curable, I believe, and Peter Vitek and a couple of other people. There is a nice new framework that looks interesting, XICC. I did not test it, but it looks interesting, and I would start with this framework if I wanted to look into this area. So I encourage you to look into it. And they have probably a pretty good simulator, because they constructed a simulator based on tensor networks, one that should be able to simulate large quantum systems pretty efficiently on the PC, even on the PC. Okay, and concluding the entire talk. First of all, I believe that machine learning might be a useful application for quantum computers in their infant state, as we can observe now. Okay, now it's pre-infant, but infant state maybe will be in like 5 years. It's not really clear if quantum computers will be useful at all yet. Nobody knows. At all. Nobody knows. I mean, of course, algorithms exist, but whether a particular algorithm, a Grover-Shultz algorithm, can be run on an existing machine, nobody knows. But I believe personally, but it doesn't mean that we should not try to work with this on this subject, because the journey towards fully usable quantum computers is very exciting, and I like a lot. I started 17 years ago, and go forward because, yeah, that's cool. This is a couple of papers and books you should look into if you want. The book, especially the book Supervised Learning with Quantum Computers, is a very interesting one. If you have access to Springer from a university, it's free, usually, in Poland. And this is a very nice article in Nature. Now it's in one in EPL that Przemek was talking about. Okay, that's one. Okay, that's my book written with my colleague, who is a mathematician and science fiction author, and a graphic designer, Katarzyna, that is circulating here. It can be bought on the internet. Basically, here you have your QR code if you want to buy it. I don't get any money from selling this book, so I can freely tell you that you can look into it if you want. And that's basically all we wanted to say. If you want to contact us, you have some information here. Thank you, and waiting for questions. General questions too.
Thanks. Okay, any questions to Piotr or also Przemek?
The website has an internet security certificate. It's not mine. It's a small bookshop in Bytom. I don't know them personally. Any open questions? Any questions just general about the subject? Would you want to give your estimate? 20 years. It's always 20 years.
Okay, it's always 20 years. So, do you think that in 20 years, quantum machine learning algorithms will be used in practice, like in actual production systems?
Nobody knows.
Like, I'm
Really?
not asking if you know, but like what you think.
No, I don't know. I don't know. I want to work on it. I want to learn more. I would like to have for this particular idea of hyperspectral image processing, my own algorithms, on our own, because it was work done with Przemek and a couple of other people. And I want to apply it to large data sets if it's possible, but nobody knows. It's a very new field. It kind of started 7 years ago, quantum machine learning by itself. In a way, probably earlier, but like 7 years ago, there was first important papers about the subject. A part of these applications we had, the quantum machine learning field is interesting by itself if you want to learn quantum information theory, proper theory. But that's a different story. That's completely different story that I don't want to talk about now.
Okay, any more questions?
Is it know how many number of, I mean, how big number of qubits is required to make it useful, I mean, the quantum computer?
I mean, yeah, in a sense, if you have, like, okay, the largest simulation we can do now, it's 49 qubits. That's what you can do. That's what you can do with one of the largest computers. Maybe you can do slightly larger using top 10 computers. But when you go further than 100 qubits, it cannot be simulated efficiently in the general case. Okay?
Do analizy spektralnej różni się od coloring problem.
Coloring?
Tak, tam te beta czym się różni na przykład?
Okay, that's a dangerous question because I have to admit here that this problem can be easily solved on a classical computer. This very particular problem, because this Hamiltonian is easy. I didn't want to go into details. We have an example of Hamiltonian that is more difficult to solve, and we can solve it too. That's slightly more complicated. But I know that D-Wave has an examples of coloring problem, and they play with this problem, and they have solutions for that. But I don't really know what's the difference between Hamiltonian. Like, they construct Hamiltonians for this problem, and they show the particular maps of US, Europe, colored using the algorithms. But the difference, I don't know. That's basically a very basic Ising model idea. But now we want to develop further. We know work on POTS models. Then it becomes more complicated, and then it's NP hard. So it's just a beginning.
Okay, thanks. Any more questions? If not, then yeah.
I wonder, most of you are machine learning specialists, so to speak, right? Or not? Because what I see here, it's every book on machine learning starts from linear algebra, but it stops just a step before what is needed to understand what is quantum machine learning. And so, because you know what is a matrix, what is an eigenvector, you know all kinds of decompositions perhaps, and you know how to apply it to optimization, etc., but you don't know how to calculate what is a unitary matrix, or how to calculate this operator e to I h times t, even if h is 2 by 2 matrix, for example. I wonder how to, whether it is really a problem, whether you feel that you don't feel at home and it stops you from understanding what is going on, because if you don't know it, you have to accept something as a belief. Including this extension of linear algebra to calculating unitary operators, right? It's interesting because there's nothing more than in physics than just this math. But it's well, an obvious question is whether you would like to see a series of videos on what this, because this is something we can generate very easily, right? You know, 5 minutes, 10 minutes Khan Academy style videos on what he really meant by calculating this evolution on, or how it works, and etc., etc. But short example problems from quantum computing, or just the physics behind this? Okay, well, that was my intuition, which was okay. We will think about it and do it probably.
Yeah.
Actually, if you're interested, I think throw into Facebook or some depository every single project that was done in the first 4 years of D-Wave in Lawrence Livermore National Lab and various other labs, and papers on all the APIs, lots more than that. So just there's lots of big body of cases.
Also, if you are interested in physics behind, even without our videos, just pick up the third Feynman, the third volume of Feynman Lectures of Physics, because it's all about what you can understand in quantum mechanics using 2x2 matrices. And all those things which were discussed here, different measurements, you know, the vertical axis projection versus horizontal axis projection, etc., etc., it is really there. I understand that you belong to the generation which prefers to see video than to read, but if you still are capable of reading, then the third volume of Feynman, if you don't bother with math, this is important, because it's very difficult to go through a problem if you have problems with math and with interpretation simultaneously. If you believe you understand math, 2x2 matrices, then go there, because it gives all the right intuitions which are needed to understand this. Okay, so
there is a Leonard Susskind's like quantum mechanics theoretical minimum. Leonard Susskind, it's called like theoretical minimum. It's very basic.
Can I return to this idea why, I mean, about mathematics behind all this stuff? So a part of learning this stuff, because it's fun, interesting, and kind of mind-blowing if you understand the physics behind, there are two motivations, or basically one motivation. One is that a lot of ideas in machine learning, such for example as tensor networks, arise from this field. So first of all, if you learn the jargon of this field, you can read a body of literature, mathematical literature, which is inaccessible otherwise. And the second, there are new ideas in machine learning arising from quantum information theory, which doesn't mean that they are connected to quantum computation strictly. They are just mathematical ideas you can apply on your classical computers, which are interesting. So there is a reason why to learn that, even though you don't want to program your quantum computers.
Can you give some examples?
Tensor networks. Look into tensor networks, looks into tensor decomposition. Those are two main subjects: tensor decompositions and tensor networks.
Generally, any algorithm is natural from the point of view of quantum computations, but maybe not so natural from the point of view of machine learning theory. Like with this example we had here, we just computed a norm between two vectors using two ways. One's on a classical computer shifting bits to the left and to the right, and the second one using physical experiment. The results should be similar. They were approximately similar, right? But it might be that there is an algorithm which better explains what does it mean that two vectors are similar or equivalent, because it's seen naturally in this language of quantum computing than in the conventional linear algebra, which is the tool for machine learning. Why not?
Okay, one more question, yes?
Oh, it's not a question. It's actually a comment.
Comment.
So, thank you. So I believe that, as most of you maybe are the data scientists, and for data scientists, I guess the best way to learn things is to see code and then see the implementation. So the next meeting will be about Rigetti, and this will be provided by Michał Stęchły. And then I guess you will learn how to implement that quantum algorithms. And I think that the math is not a problem, because most of the data scientists know what is linear algebra. It's how to construct the quantum algorithms from the elements of that linear algebra. And I'm just hoping that next time Michał Stęchły will explain the basic components and show some code actually.
Yes, that's right. So far we've learned a bit about the theory and what we can do with quantum computers, but indeed 2 next lectures will be dedicated to programming quantum computers using Forest programming language. So yeah, Michał Stęchły next time will give us introduction, and also later David will show how to implement Grover algorithm, right? maybe, or another algorithm. We'll see. And also, if you're interested in applications of quantum computers in AI, and or also applications of AI machine learning in quantum computing, because there are also such applications. Last week or 2 weeks ago, I was in Montreal attending Europe's conference, and there was one paper authored by Scott Aronson and some people from Google, when they indeed applied machine learning to quantum computing. So there are also such applications. You can also join Quantum AI Facebook group, which we run. There are more than 500 people there from many countries. So we also publish articles, links to some interesting papers, and so yeah. So you can also contribute or just participate in discussions and learn. Yeah. So then right now there are really many sources to learn about quantum machine learning and quantum computing in general.
Finally, there is a hardware, and although probably nobody here builds quantum computers, Grzegorz Kasprowicz group at Institute of Electronic Systems at Warsaw Technical University works with all big shots on producing high-speed electronics, which controls all those experiments, aka quantum computers. So actually we are closer to the matter than you may. It's not that a black box are being sent to us and we are just, treating it as a black box, but parts of those things are actively developed in Warsaw.
Okay, thank you. Any more questions or comments? Yes, one.
So currently, what is the level of noise in these real machines?
I don't know. I mean, they give some parameters, of course, and it depends on the time of the day. In fact, there is a paper by Juli group in Germany that assess the reproducibility of algorithms using these machines in IBM or Rigetti. Basically, there's a lot of noise. Unfortunately, way too much.
Maybe one comment. First of all, when you use D-Wave, it never gives you ground state. It usually is an optimization problem that has got lots of solutions, and of course you probe the space of solutions. So statistically, one of the solutions will be a pretty good one, and in practical problems, it's the type of solution that should be satisfactory. Going back to the sort of Ising model, which is the basis of D-Wave, so the trick in programming is to reduce your problem to Ising problem, and this is Ising model on square grid. Most probably, if you look at the topology of this interconnects, but it may turn out that your problem is lower dimensional Ising, and you mentioned Potts model, and there's Hadamard model. There are all sorts of statistical models, and it turns out that depending on dimensionality of the problem, some of those problems are exactly solvable. So I recommend reading book by Rodney Baxter, a classic, exactly solvable models in statistical physics. And you see that, for example, something reduces to one-dimensional Ising model, forget quantum computer. It has got closed solution in algebraic form.
Okay. Any more questions, comments? If not, then once again, big applause to our great speakers, Przemek and Piotr. Okay, so we can be here in Przestrzeń from Facebook until 10 p.m. So we have about half an hour. So yeah, we can still discuss some ideas if you have time and if you want to stay. And as I said, the next meeting will be in January, probably 28th, but it will be confirmed. Thank you once again for your attention, and see you next time.